Okay, so in the previous lecture, we were doing a problem, and that particular problem consisted of a Cauchy-Euler differential equation. So this is sometimes called as a Cauchy-Euler differential equation. And this was a homogeneous Cauchy-Euler differential equation that we were doing using this Cauchy-Euler differential equation. We were doing using, and we were constructing, a Green's function for the same. And given the boundary condition that yx must be bounded as x tends to 0 and y1 should be equal to alpha dash y1, given that y alpha is not equal to 0. So all these given conditions, we were able to find Green's function, and these a, b, c's values I'm going to list shortly. So this will be like the first thing is given to us is b is equal to 0. So if my b is equal to 0, I have to forget about this particular factor. Also given that your c is equals to alpha d, and fourth condition was given to you was gx zeta plus comma zeta minus gx zeta minus comma zeta is equal to minus 1 upon zeta. If I want to solve it, how would I solve it? So if I keep my b equal to 0, at least some part will be fine. So this will be, I think, this. See, what I want to suggest is that if you just readily place b equal to 0, b equal to 0 itself in the very first thing, then your g would reduce itself to a, and you have simply c plus d ln x. Is that clear to you? This is what I want to say, so that it reduces some of your problem. Okay, now at zeta plus what we want, zeta plus is this, so I have to differentiate it. So I will differentiate it. This will be equals to I think minus 1 upon zeta. Why this will be equal to minus 1 upon zeta? Because this particular thing that is to the left, you have only one constant left. And you have, if you have only constant left, then this derivative would be 0. Is that clear?
Yes, sir. C will also not come, sir.
Sorry, C will also not, because the derivative is 0. So this suggests that my D should be equal to minus. Is that clear?
Yes, sir.
And if my D is minus 1, then C would be equal to, I think, minus alpha. That
yes,
is also clear. And if my C is equal to minus alpha, D is equal to this, I have found that B is equal to 0. And then I can also find my A also. See, A would be equal to what? So B is 0, forget about it. C is minus alpha, D is minus 1. So my A would be, I think, some negative. I'll take common. This will be alpha plus ln zeta. Is that clear?
Yes,
so this
sir.
is your A.
Yes.
So all these terms are now clear. So you can now write your Green's function, which happens to also solve this particular differential equation. It's a solution of a differential equation also, no? Right? This Green's function is also a solution. Sir. So this will be from 0. Why I'm not writing exactly equal to 0? Because that is ln x. So now I can write, because initially I was not able to write because there was some ln. Now we have used this boundary condition that my function should be bounded. So my function should be bounded as x tends to 0, implies I cannot have this logarithmic term in my definition. So now I can even include this 0. Is that clear?
Yes, sir.
I'm left with only constant, isn't it? So your constant is, I think, minus alpha plus ln zeta. And then you have from zeta line from, I think, x line from zeta to 1. And I think this particular expression you can write c
minus 1 plus alpha.
Sorry if I'm not wrong. So minus alpha and minus ln x. Is that clear? If I'm not wrong. So you can take negative also common out and you can write. So this will be your Green's function for the given Cauchy-Euler differential equation. Is that clear?
Yes, sir.
No, these were the cases when we had, then we had, you can say, a homogeneous case. Now, what about inhomogeneous case? So whenever your function.
Yeah, bete.
हाँ बेटा बोलो.
Yeah, bete. Oh, sorry.
ये सही तो है ना?
हाँ जी सर सही.
एक नेगेटिव और कॉमन ले सकते हो बाहर पूरा, but overall this is fine. Okay, so I think I hope I have given you some introduction to your construction of Green's function for homogeneous differential equation. Now, if my differential equation is slightly now if it has some kind of forcing term, you can say, or you can say that if there is some homogeneous term. Why I'm saying forcing term? Because if you study the theory of oscillations, you have some damped oscillation, then you have something called as forced oscillations, where you are forcing, you can say that function happens to be on the right hand side. If you remember, then there is some forcing function also. So if you have this kind of forcing function, or you can say some function here, then those differential equations are also called as inhomogeneous differential equation. In these particular cases, the the thing called as Dirac delta function returns. Okay, so again there's again Dirac delta function here, and I will let you know all these things in a different lecture. I told you that I'm going to take a simple lecture, only a 40-minute lecture on generalized function. Just what do you mean by generalized function? So there you will understand why Dirac delta function is called as generalized function, why again Green's function come in those categories. Okay, but overall, whenever you replace this zero by some function f of x, then this particular differential equation is called as your inhomogeneous differential equation. And inhomogeneous differential equation with initial boundary conditions, how to solve and how to write a Green's function for them, I'm going to discuss now. Is that clear till now?
Yes, sir.
Okay, we'll do quite many questions. You also do quite many questions. I think where I'll find some questions, or I'll share you some questions. Group itself. Mostly do like whatever has come in your net examination, at least do those problems so that you develop some confidence. Okay.
Yes, sir.
Okay. So where was I? So so construction of Green's function for inhomogeneous or non-homogeneous, you can say, differential linear differential equations. So now let us consider your Ly to be written as f of x. L here represents your a naught d by dx to a1 d by dx plus a2. So now L represents your a naught d2 upon dx2 plus a1 d by dx and a0 a2, sorry. So this is your linear differential operator. Now if you have this particular differential equation, second order homogeneous linear differential equation, I think I wrote some p naught p2, so I'll use those only. So if I had this particular differential equation and given conditions that alpha ya minus beta y dash a is equal to 0 and gamma yb minus delta y dash b equal to 0, then Green's function is a solution of an impulsive equation. What do I mean by impulsive equation? Solution of an impulsive equation where your source function is replaced by a Dirac delta function. So what happens is, I'll say that if given this differential equation, I can write the solution of this particular differential equation in terms of I can write using a Green's function. But first we have to find what would be the Green's function. So Green's function would be nothing but the solution of this particular differential equation had this fx being replaced by a Dirac delta function. So I'll write it right away here. So Green's function is a solution of an impulsive equation given by Lg is equals to Dirac of x minus zeta. So here it is. Okay, here it is. So if again I'm reiterating, if I am given a linear differential equation, non-homogeneous case, what will happen in order to write the solution of this particular differential equation via Green's function? First, we have to find the Green's function, and the Green's function would nothing be but be equal to what? But it would be equals to the solution of this particular differential equation had this fx been replaced by your Dirac delta function. Is that clear?
Yes, sir.
Okay. So for differential operators satisfying Green's function, you'll quite often see this Dirac delta function appearing. So for Green's function of differential operators, we'll quite often see this kind of functions, that is Dirac of we will see Dirac delta function appearing on the RHS of these differential equations. Okay, and certainly this will be of great help. See, for example, even as simple as your del square phi that we were discussing yesterday and that we'll discuss tomorrow also, you'll see that how this particular differential equation, for this particular differential equation, which is your Gauss law, or sorry, whatever you say, like I think you say it as a Poisson equation. So for Poisson equation also, we'll construct some green function. So all these things we're going to see in the later lectures. But overall, first thing is to write the Green's function. So I'm not getting into the derivation part. What is Green function? How it would have been derived. But we are using Green's function in order to solve these boundary value problems. Is it clear to you? Now let us find some Green's function for the same. And the properties Green's function would remain the same. So Green function would satisfy all the other properties. All the other means the first property has been altered. Now, no longer your Green's function is the solution of the differential equation. Rather, your Green's, if you want to find Green function, your function should be replaced by some function which is concentrated at zeta. I'll let you know all these things. Don't worry about it. Probably tomorrow itself, I'll give you an example, a basic example of what you say. If you are aware of something called as deflection of a perfectly elastic string. So deflection of a perfectly elastic string under action of a concentrated load. So if there is a load on a perfectly elastic string, and how to find that deflection, you'll see that solving that particular problem itself would, is a major motivation, which can result into a better understanding of this function. So that we'll do tomorrow. But overall, understand that Dirac delta function would come instead of your f of x. So instead of f of x, now you will have a Dirac delta function. Okay, so here first property, except first property, so that is all the properties from 2 to 4. What were 2 to 4? The second property was, I think, this that your Green's function would satisfy the boundary condition. The third property was it would be a continuous function. Fourth property, that there would be a jump discontinuity in the first order derivative at zeta. And that you can also see. So for example, now here it is quite inevitable. See, here it is quite evident also, and it's quite inevitable also, since we've seen that whenever we had this, whenever we were solving some differential equation, which had something to do with Dirac delta function, you could see that all those differential equation, in all those differential equation, your first order derivative suffered a discontinuity at the source of the Dirac delta function. If you remember, when we were doing Dirac delta potential in quantum mechanics, or anywhere, I mean, anywhere you could see that whenever you had this source, this Dirac delta function sourced at some point, and if you want to solve the second order differential equation, your first order derivative becomes discontinuous, isn't it? If you remember. Bharat, are you there? Are you not there?
Yes, sir.
Yeah, there. When we were solving, like, what I could say, Dirac delta potential, if you remember.
Yes, sir.
So whenever you had this kind of source centered at zeta, at those points, your first order derivative of the desired function was discontinuous, if you remember.
Yes, sir.
So this is certain motivation also giving you. I'm going to come to all these things as and when we are going. So let us do a few problems and understand how to construct a Green's function for. Let us start with a very simple problem, and let us construct a Green's function for. Construct a Green's function for. Let us construct a Green's function for a problem. Let's say this.
So this Dirac delta function appears, this form appears for non-homogeneous equations only.
For non-homogeneous solution, not for homogeneous case. However, for homogeneous case also, you will find that your gx suffers a discontinuity. The derivative of gx also suffers a discontinuity at zeta.
Yes.
So there I'm not able to link it, but here I'm able to link it somehow. I'm just able to explain you. I'm just trying to remind you that certainly these things you have seen. Like whenever you have you have something to do with Dirac delta function in linear differential equation, you see that there is a discontinuity in the first order derivative. If you remember the
Right.
Schrodinger's equation we were solving for repulsive and attractive Dirac delta differential. So you could see that there was a jump discontinuity in the derivatives. And that is why I told you that the second order differential equation is defined, but the first order derivative has some discontinuities. And such solutions are called as weak solutions in mathematics.
Right,
If you
sir,
remember,
right.
this is what I was telling. So this is a this is a differential equation. This is clearly a non-homogeneous differential equation of second order, and linear differential equation of second order. And this is a non-homogeneous case, and we want to construct a Green's function for the same. So how to construct a Green's function for this particular differential equation? We have to see. Okay. So the first thing that we have to see is that Green's function would cancel again. Okay. So Green's function now would satisfy the Green function would now satisfy the differential equation given by d2y upon dx2 minus y is equal to Dirac delta x minus zeta. Is that clear? And we know that whenever you have this Dirac delta function, what you can do, you can write solutions only if x is not equal to zeta. Because if x is equal to zeta, then things will be difficult for you. Is that clear? Because
Yes,
at x
sir.
equal to zeta, there is a infinite kind of jump. So you cannot write. So if x is not equal to zeta, then what will be the solution? So solution would correspond to d2y upon dx2 minus y equal to 0. So simply, if x is not equal to zeta, this particular differential equation, solving this particular differential equation, satisfies. So I'll write g, I'll write g, I'll write g, I'll write g. Okay. So this will amount to solving differential equation, which is a homogeneous kind. I mean, like x has been removed, x has been replaced by Dirac delta x minus zeta. And as I know that this cannot be solved for x equal to zeta, what I would do, I'll write x not equal to zeta. I will try to solve this differential equation. And this particular differential equation, you know that solution would be some exponentials, isn't it? So I will write simply some a e की power minus x. Let us write it first. So let us write some a e की power x plus b e की power minus x, and then I will write c e की power x plus d e की power minus x. For all x not equal to zeta means forget about zeta, but otherwise for all zeta other than x other than zeta, you will have these solutions. Is that clear to you? So
सर
instead
ये
of
जो जीरो
हाँ बोलो
जीरो और वन के बीच में हम जीटा ले रहे हैं, ये क्वेश्चन में मेंशन्ड है, इसलिए बाउंड्री वाली प्रॉब्लम के उससे ले रहे हैं ना, जीरो और वन के बीच में फंक्शन।
हाँ हाँ बिल्कुल 0 और 1 तुम यहीं से पता कर पाओगे. लाइक जो भी तुम्हारे यहाँ इनिशियल कंडीशंस दे रखी होती है ना, वही फिर ए और बी बनते हैं. आर गेटिंग?
ओके
तो
सर.
यहाँ से पता लगेगा. y0 y1 equal to 0 दे रखा है ना. So initial conditions are mentioned at point 0 and 1. Is that clear? So from here you will get an idea
Yes.
of what is 0 and what are your a's and b's, or where your differential equation is defined. So basically your differential equations is defined at least for all values between 0 and 1. So because the conditions are given on 0 and 1, so that will decide your these bounds. Is that clear?
Yes, sir.
Otherwise people would write your differential equation so and so is defined on like while writing this, they will say that your x lies between 0. Ideally, they should write this, and then they give the condition. Is that clear? So here, by only these things, I'm able to figure out. But otherwise, whenever a differential equation is given, alongside we are given the interval of existence of that particular differential equation. So don't worry about it. Okay.
Okay.
I hope it is clear. Okay. So देखो x not equal to zeta, we have written the solution. Now we know that my gx comma zeta would satisfy the what you can say the boundary conditions. And the boundary conditions are given by y0 equal to 0. So that implies g 0 zeta equal to 0, and g0 zeta would be equals to what? It will be equals to a plus b equal to 0. This is my first condition. And second condition would be, I think g1 comma zeta would be 0, because the second condition is y1 is equal to 0. So that will be giving me c plus d equal to 0. Is that clear?
Yes,
And
sir.
I think third condition, मैं कुछ गलत लिख दिया क्या? c plus d नहीं होगा, c plus यहाँ पर e आएगा और यहाँ पर b आएगा. So that will give me ce plus de की पावर -1 would be 0, and that would give me, I think, इसको देखें तो minus d e की पावर. So I think, is that clear? मतलब इसको यहाँ divide कर दो. So this e square c would be equal to minus d. Is that clear? ये दोनों conditions satisfy होंगी क्योंकि these are the boundary conditions. These are the boundary conditions given to you. Is that clear?
Yes, sir.
इसका मतलब क्या हुआ? It implies that your g as a function of x comma zeta, simply I can write as, I think, a e की power x minus a. I will write minus e की power minus x for all x lying between zeta and 0, and for all x lying between zeta and 1, I can write it as c e की power x, and you had, I think, minus. Is that clear? I think this is clear. E square, this will be e की power minus x ना यहाँ पर, तो d की जगह लिखेंगे e square c, and c is taken from around. Now I think this is clear.
Yes.
If I have to see further that your g x comma zeta must be a continuous function. So in the half intervals, that is, here you have some linear combination of e की power x and e की power minus x. Here it is continuous. Here it is continuous. The problem of continuity may arise at zeta. So I will find whether my function is continuous at zeta or not. So that will give me a e की power zeta minus e की power minus zeta must be equal to c e की power zeta minus e की power 2 minus zeta. Is that clear? And if I solve it, solve तो क्या कर पाएंगे इसको, लेकिन at least write it in some format. I think this will be, if I write it there, so it will be c minus a e की power zeta would be equals to, if I bring c here, a उधर क्या है, सबको इधर ही ले आओ. So what you'll get, plus c e square minus a e की power minus zeta is equal to. Is that clear? So c minus a e की power zeta plus c e square minus a e की power minus zeta equal to 0. Sorry, right? So this is what we'll get from the continuity thing. Now further, there is a jump discontinuity. There is a jump discontinuity at x equal to zeta for the derivative of the Green's function. Is that clear? So your derivative of Green's function at zeta plus comma zeta minus, this will be equal to what? Minus 1 upon p naught zeta. And what is p naught here? So let me find what is p naught. So p naught will be the coefficient of the highest order derivative. This is, I think, 1. Is that clear? I hope it is clear.
Yes, sir.
So what I will write, let us take the derivatives. So what are the derivatives? थोड़ा सा इसको देखना पड़ेगा वापस से. इसको देखते हैं, ठीक है? Now let us write the derivative. So derivative क्या होगा? The derivative will be, I think, c e की power zeta, e की power zeta. I think it will be it. And to the right ना, तो इसका derivative कितना होगा? I think again minus plus c e की power 2 minus zeta. Is that clear? अगर इसका डेरिवेटिव करेंगे तो c e की पावर x.
Yes, sir.
इसका डेरिवेटिव करेंगे तो, हाँ बेटा,
Minus. सही है, sir.
सही है ना? And then there will be minus derivative on the left. Derivative on the left क्या आएगा? a e की पावर x, तो I think ये आएगा a e की पावर zeta and plus
Yes, sir.
minus. Is that clear? So if I want to write all these things up, ये क्या आएगा c minus a e की पावर zeta plus uh, I think this will be c e square
माइनस ए
minus a e की पावर
माइनस जीटा।
minus zeta, है ना? a होगा।
यस
तो
सर।
गलती तो नहीं कर रहा हम करने में, प्लीज चेक करो, अदरवाइज इफ वन मिस्टेक विल डू देन विल रिपेंट फॉर इट फॉरएवर। So like c minus a e की पावर zeta, ठीक है, जो भी, आई थिंक इट इज क्लियर, ये आ रहा जो आ रहा है, ठीक है, डन। सो दिस इज हाउ इट इज नाउ, लेट अस थोड़ा सा सॉल्व करना ही पड़ेगा, मतलब अच्छी है तो है। सो व्हाट आई विल गेट इज, we already have certain conditions that are given to us. Achha, these are the conditions that are given to us. C minus a e की power zeta plus c square minus a e की power minus zeta equal to 0 also given, and here it is given 1. So what should I do?
सर ऊपर ना माइनस गड़बड़ है, ऊपर वाली क्वेश्चन।
अच्छा, यह माइनस आएगा।
मतलब अंदर माइनस ए की जगह प्लस ए आएगा और सी
हाँ हाँ
स्क्वायर
हाँ,
के आगे
सॉरी
माइनस।
सॉरी सॉरी, क्योंकि इधर की तरफ आएगा ना।
सब कुछ आप लेफ्ट राइट साइड में ले गए थे ना।
हाँ, अपन लोग राइट में लेके गए ना, तो ये आएगा a एंड ये आएगा माइनस, राइट? ऐसे कहना चाह रहे हो ना,
हाँ जी सर।
है ना? तो a माइनस, हाँ अब हो जाएगा, अदरवाइज वो दोनों इक्वेशन पैरेलल हो रही थी, मैंने कहा ये क्या होगा। चलो इन दोनों को घटाएं अपन दोनों। सो फॉर एग्जांपल इफ वी ऐड दीस टू अप, if we add these two up, what I will get c. So if I add this equation and this equation, I should have number them up, so I'll number them. So I think this equation I give it a number, let's say 1, and let's say I give this equation number 2. So if I add equation number 1 and equation number 2, so this will go away, and what remains is c
ऐड
minus, हाँ बेटा बोलो।
मैं बोल रहा था ऐड करने की जगह सब्ट्रैक्ट करेंगे तो एक टर्म कैंसिल नहीं हो जाएगी पहली वाली।
देखो अगर तुम ऐड करोगे तो आई थिंक दिस a minus c e square e की पावर minus zeta, and this is c e square minus a, so this will get cancelled.
हाँ ये सर।
तो बचेगा क्या, c minus a e की पावर zeta is equal to -1, or I can write that my c minus a is -1 upon e की पावर zeta. This is my equation number 3, let's say. Is that clear? And if I subtract these two up, so if I subtract these two up, so what I would get, I would, if I subtract 1 from 2, so हाँ बेटा बोलो।
विल गेट अ फैक्टर ऑफ 2 आल्सो सर, जब ऐड करेंगे तो 2 टाइम्स।
हाँ सॉरी, 2 also, sorry, we'll get 2 times, so I'll write 2 here, ठीक है? So if I add these two up, and if I subtract 1 from 2, so 2 में से 1 घटाएंगे तो कितना आएगा, c e square minus a e की पावर minus zeta, and minus minus it will become plus e की पावर, if I subtract, ठीक है, this will be equals to minus, ठीक है? So overall it will give me minus, what I देते हैं, so overall it will give me a minus c e square is equal to 1 upon e की पावर zeta. So this is my equation number 4 and 2 also. So 1 upon 2 e की power minus zeta. Is that clear to you? This will be your equation number 4. Okay, so you have two equations in A and C. And you have two equations in A and C. I hope we can find the solutions for A and C using 3 and 4. Is that clear? And I think we had only A and C left, because all other things we have done. We have solved this D and all those things. So only we are left with A and C, right? Is that clear to you?
यस सर।
Okay. So if I just try to solve it, so what I will get, if I want to find A, so I just need to multiply with E square, right? So just find me A and just find me C. So if I just multiply with E square and just give me the answer. एक आंसर बताना, मैं तब तक I'll solve it separately and I'll. So what? Because the book's answer has been given in some hyperbolic form, so I hope I will have to see. इसको कर ही लेते हैं. C e square minus a e square is equal to minus e square upon 2 e to the power c. And you just add these two up, so you get a 1 minus of e square is equals to 1 upon 2 e to the power c. Okay, so I think you will get a as, if you just divide it, so a will come as 1 upon 1 minus of e square, and then you will have, I think, if I take 2 also common, so I will take 2 also common, so you will get, I think, e की power of uh, uh, e की power of, अच्छा, this is zeta, no, sorry, so this is e minus zeta, so you get e की power minus zeta, so this will be, I think, e की power zeta, and then you will have a term minus e की power of minus zeta plus 2. Is that clear? So you have this 1 upon 2 e 1 upon 2 1 minus e square e की power zeta minus e की power minus zeta plus 2. And what would be your c? C would be equals to c would be equals to what? C would be equals to 1. Sorry, I'll write it as e की power zeta e की power zeta upon 2 minus में and then plus e and then 1 upon e square. Okay, so this is what I'm going to write. So this will be like 1 upon e square and then just try to write a also. So c will be equals to what? Just take LCM of it. So this will get cancelled. And this e square also will get cancelled. Here you have e square, here you have e square. So effectively, you are left with, I think, c is equal to 1 upon 2, 1 minus e square. And you are left with e की power minus zeta minus plus e की power zeta. And I think this forms sine hyperbolic. So overall, okay. So overall, my c happens to be, I think this is sine hyperbolic zeta into 2 and when divided by 2, 1 minus e square. Is that clear? So your c is sine hyperbolic zeta upon 1 minus e square, and your a happens to be this entire thing. So I'll write again, a is equals to what? A is equal to 1 upon 2 times 1 minus e square, and then you had some e की power, uh, what was there? I think zeta minus e की power minus zeta plus 2, and then you had c is equal to sine hyperbolic zeta 1 minus e square. So your solutions to a and c are there, and your Green's function was, I think the Green's function is given by gx comma zeta was given by, I think it was some if I correctly remember, it was twice a. It is like a e की power minus x, and this I can write as sine hyperbolic x, isn't it? So I can write it as 2a sine hyperbolic x. So I can write it as 2a sine hyperbolic x, and for all x lying between zeta and 0, and for all x lying between zeta and 1, it was, I think, some very trivial. Okay, so just you have to replace e की power x minus. So second thing you have to write c e की power x minus c e की power
2.
Is that clear?
Yes, sir.
Okay. And so we have to just express these things. Okay. Is that clear? A I have already written in this form.
Yes,
Can I
sir.
just modify it in some sine hyperbolic form also? So A was what? A was, I think,
A is equal to 1 upon 1 minus e squared.
you just try to write A in some forms. I think answer is not exactly this. Some different answer is given in the book. So just try to write somewhere like एक काम करते हैं ना इससे. You just take, I think, some, what should I say? You take some. अच्छा एक काम करते हैं. According to the, so what is sine hyperbolic 1? Sine hyperbolic 1, I would write e की power 1 minus e की power minus 1 upon 2. So I can write it as e square minus 1 upon twice e, isn't it? This is something that I can do. So I can write that my 1 minus of e square would be equals to minus 2e sine hyperbolic 1. Is that clear to you? So if you write this 1 upon like this thing in format of this, so what I would get? I will simply get my a further can be simplified as, a can be further simplified as, I think, 1 upon, instead of this, I can write minus 4e sine hyperbolic 1. Is that clear?
Yes.
Your a can be written as this way. And if I want to write your 2a sine hyperbolic x, then I can write it as, I think, 2a. अच्छा अच्छा, a ऐसा थोड़ी था, a क्या, ये भी तो था टर्म. There was another term.
Yes, sir.
e की power
E to the
zeta,
power x.
sorry, e की power zeta minus e की power minus zeta plus 2, isn't it? ये भी तो टर्म था. So 2a sin hyperbolic तो बाद में लिखेंगे, पहले देखो a ये हो गया, और इसमें से क्या कॉमन ले सकते हैं? What we can take common out is, I can take common out is, this was, I think, minus zeta plus 2, and this is like a combination. Let us all the more simplify it so that a would eventually come out as minus 1 upon, मैं एक बार वापस लिखता हूँ, 4e sine hyperbolic 1, और a काम करते हैं, this e I will divide inside, so I'll write e की power zeta minus 1 minus e की power minus zeta plus 1. Is that clear? है ना? थोड़ा सा अगर इसको थोड़ा ध्यान से देखोगे तो isn't it equals to 2 sine hyperbolic zeta minus 1, है ना? Because I mean, if you take zeta minus 1 as 1 and this is negative of zeta minus 1, so I would write it as minus 1 upon 2 sine hyperbolic 1, and inside I would write sine hyperbolic zeta minus 1. Is that clear? So this is how it is given in the, so a is given like in this format. थोड़ा सा और आगे solve करोगे तो this is how you get. So a you have to replace here in this fashion. Is that clear to you?
Yes, sir.
And similarly, if you work with the c also, you will get some values. So your c would eventually come out as, your c is sine hyperbolic 1 upon 1 minus of e square. You just solve it somehow. So I think this will also be what you got. C was given as 1 upon 1 minus of e square sine hyperbolic 1, isn't it? ऐसे कुछ था, sine hyperbolic zeta square. So you can write 1 minus of e square in the format of sine hyperbolic 1. So eventually you will get this as an answer. Is that clear to you? So if you write here in terms of sine hyperbolic, you can replace this particular thing here. Is that clear to you? So overall, this forms the solution of your inhomogeneous differential equation. So this is your Green's function. Is that clear?
Yes, sir.
we'll do quite many questions, and we'll also see how to form the solution of the differential equation using the green function. In inhomogeneous case, for homogeneous case, your G itself was a solution. Now for inhomogeneous case, what to do, that we'll see in lectures tomorrow. Till now, I think it is clear. It will take